So hi everyone, in this video, we are going to talk about sequences and summations. In the previous materials that I have given you, we have discussed basically about functions and some kinds of functions like the injective, surjective, and the bijective. So for today, our topic will be about sequences and summations. So one of the most important tasks in math and of course in computer science is to discover and characterize regular patterns, such as those associated with processes that are repeated. So the main mathematical structure used in the study of repeated processes is the sequence. Okay, so suppose we have a person and that person decides to count his ancestors. So that person, or us as a regular person, we can have 2 parents and 4 grandparents, 8 great grandparents, and so forth. Okay, so this can be written in a row as 2, 4, 8, 16, 32, and so forth, wherein the 2 here represents the number of parents of that person, the 4 represents the number of grandparents, the 8 represent the 8 grandparents, and so on. So this symbol is called an ellipsis, and it is shorthand for and so forth. So to express the pattern of the numbers, suppose that each of this number is labeled by a certain integer that gives its position in the row. So as you can see here, 2 is in the first position in the row, 4 is in the second position in the row, 8 is in the third position in the row, and so on. So, and we can also see that the number that is corresponding to position 1 is 2, okay? And which is equal to 2 raised to 1. And the number corresponding to the second position in the row is 4, which is equal to 2 raised to 2. So for positions 3, 4, 5, 6, 7, 8, and so on, so the corresponding numbers are 8, 16, 32, 64, 1 to 8, and so on, which equal to 2 raised to 4, 2 raised to 5, 2 raised to 6, 2 raised to 7, 2 raised to 8, etc. Okay, so what we can see here is that for a general value of k, let a sub k be the number of ancestors in the kth generation back. So the pattern of computed value strongly suggests the following for each k. So for each k, we have a sub k is equal to 2 raised to k, wherein the k in this kind of example will basically refer to the position in the row. All right. So now that is an example of a sequence. And a sequence is a function whose domain is either all of the integers between 2 integers or all the integers that are greater than or equal to a given integer. So we typically represent a sequence as a set of elements written in a row. So in the sequence denoted as a sub m plus 1, a sub m plus 2, and till a sub n. So each of the individual element a sub k is called a term. So a sub m is a term, a sub m plus 1 is a term, a sub m plus 2 is a term, a sub n is a term. Okay, so the a sub k, it is referred again to as a term, and the k is called as a subscript or an index. So in this case, in this sequence, the m, which may be in any integer, is the subscript of the initial na term. Okay, and the n, which must be greater than or equal to m, must be greater than or equal to m, is the subscript of the final term. So if we have this notation, a sub m plus 1, a sub m plus 2, and so forth, we are basically denoting here a infinite na sequence. Okay, so in this case, what will be the terms? The terms will be a sub m plus 1 to a sub m plus 2, and so forth. Okay,